hydrogen. Now, if we have more than one alpha hydrogen in there, in all of these cases, we are considering a symmetrical carbonyl where the base has just one alpha hydrogen to pick. If we have systems that have more than one alpha hydrogen, then in this case, what is going to determine what alpha hydrogen is abstracted by the base is two things. It's the type of the base and the solvent that you are using. So if you're using small bases, these are the small bases in there, then the solvent that you need to use is a protic solvent. We talked about protic solvents in organic 1, and we said that these solvents, they have OHs and NHs, okay? And they're like any alcohol, like any water, like ammonia, for example, all of those are considered to be polar protic solvents. When you see a polar protic solvent with a small base, then in this case, those bases are going to target the most substituted alpha hydrogen. Bulky bases are two types, oxygen base and nitrogen base. For nitrogen bases, those are going to work with an aprotic solvent like acetone, like THF, and they're going to attack the less substituted alpha hydrogen. Normally, LDA works at a low temperature. Potassium tertiary peroxide works at a high temperature. So this is why whenever we are working with LDA, LDA always is going to form the kinetic product. And potassium tertiary peroxide is going to form the thermodynamic product. Okay, so let's go ahead and have an example. Whenever you are using LDA, we're going to couple always LDA with a polar aprotic solvent. We're going to use it at a low temperature. In there, LDA is always going to attack the less substituted alpha hydrogen. So over here, this is going to be the less substituted alpha hydrogen. This is a strong base. So that base is going to come, take the alpha hydrogen and create the enolate ion in this case. The enolate ion will undergo resonance. I am not showing the resonance here because the reaction has a continuation. This is the first step of the reaction over here, and this is the second step. The continuation is that the enolate now, it's going to serve as a very good nucleophile. Why it's a good nucleophile? It's a good nucleophile because it is a negative charge. This is a strong nucleophile. So that strong nucleophile can undergo an SN2 reaction. And SN2 reactions, they happen with methyl halides, primary and secondary alkyl halides only. Remember, they cannot happen with a tertiary alkyl halide. So if you have a tertiary alkyl halide, there will be no reaction in there. So all what I did over here is I simply added to the alpha carbon an R group. This is called an alkylation reaction at the alpha carbon because you alkylated or you added an R group at the alpha carbon. This is the overall reaction, and the reaction is two steps. First step, base comes, forms the enolate. Second step, the enolate comes and attacks the partial positive carbon, which is this carbon over here. This is the partial positive carbon. This is organic 1 SN2 reaction. So when it attacks the partial positive carbon, the bromine is going to leave. It is a simple SN2 reaction, and please put this as a note that SN2 does not work with tertiary alkyl halides. So let's say, for example, if we have this reaction over here and we are reacting this with LDA. This is the first step. Let's do LDA, THF, and minus 78 degrees Celsius. This is the only alpha hydrogen on the side. On the other side here, there is no alpha hydrogen. So the base is gonna come, is gonna take that alpha hydrogen and create the enolate. So you make your enolate ion. You can go ahead and allow the enolate to undergo a resonance in there, or you can go ahead and skip the step and introduce the negative charge on the oxygen. Both are considered to be enolates, so both are going to be enolates. But normally, since I'm working with a basic medium, I would prefer that you keep your negative charge on the carbon rather than on the oxygen, so that you would know that this is your nucleophile in there. Now, the next step of the reaction, this is going to be step 2. Let's say, for example, if I am doing tertiary butylbromide, well, there will be no reaction. I know that this one is going to be a strong nucleophile, but this is a tertiary alkyl halide. And if it's a tertiary alkyl halide, there will be no SN2 in there, so there will be no reaction. Let's have another example over here. Now we are using small bases with protic solvents, or the bulky potassium tertiary peroxide with a protic solvent. In this case, your product is going to be a thermodynamic product. So these are going to form the thermodynamic product. And the thermodynamic product is the attack on the most substituted hydrogen, alpha hydrogen in there. So the base is going to come, take the most substituted alpha hydrogen and create the enolate, and then you're going to end up having a reaction in there with any alkyl halide, any methyl, primary or secondary. This one is a methyl halide, so the reaction can easily work. And you here, all what you did is you added an R group on the alpha carbon, and the R group is the CH3. Another example there, LDA. LDA is going to attack the less substituted alpha hydrogen, but here I don't have any other alpha hydrogen. This is my only alpha hydrogen. So the LDA is going to come, take it, make the enolate. These are very simple, straightforward reactions in there. And then your nucleophile is going to attack the sp3 hybrid. It has to be an sp3, you guys. You are doing an SN2 reaction after all. So this is an sp3 hybrid carbon. It's the carbon which is directly connected to the bromine, and the bromine is going to leave. This is a primary allylic alkyl halide. The reaction can work, and I am forming a bond between this carbon and this carbon, the rest of the molecule in there. This is another example in here. Again, you are alkylating at the alpha carbon, and you are adding an R group. Multiple step reactions with the enolates. So you start with the base, attacking the only alpha hydrogen and create your enolate. Make sure that your alkyl halide is suitable for an SN2 reaction. So here I have an SN2 reaction. It is a methyl halide. It can work. You will end up adding a CH3 over here. So our first two steps, you alkylated on the alpha carbon, you added a CH3. Now you can change the ester into an acid. This is hydrolysis of esters in acidic medium. Refer to chapter 19, please, for the mechanism of the reaction. Every single ester, if you have more than one ester, all the esters are going to turn into a carboxylic acid. This is acidic medium, so you're going to form a carboxylic acid in there. And this is going to be your final product. Now let's have another example. Now here I'm having 4 steps in there. I'm using sodium ethoxide. This is a small base, and it's going to attack the most substituted alpha hydrogen. But here I have only, again, one type of alpha hydrogen, and this is the most acidic alpha hydrogen here. So the base is going to come and take one of these alpha hydrogens and create the enolate. Once it creates the enolate, I'm going to react it with the alkyl halide. And again, please pay attention that the attack is on the partial positive carbon so that the bromine can leave. Okay? So you're going to attack the partial positive carbon. It's this carbon over here. And what you are adding on the alpha carbon is a chain of 1, 2, 3 carbons in there. So this is going to be my alkylated chain that is added on, or my alkane chain that is added on the alpha carbon. Now, after I do this, I'm going to do hydrolysis in basic medium in here. I could do hydrolysis in acidic medium. I could combine both of these steps in water in presence of H plus. So, but here I'm just showing you that I can do hydrolysis in basic medium and then do or add an acid, or I can simply do hydrolysis in acidic medium. Both are going to end up being the same, hydrolyzing both esters into a carboxylic acid. So hydrolysis in basic medium is going to end up forming the carboxylate, both the O negative in there, and then adding an acid, you're going to add an acid or a hydrogen to each one of these carboxylates. Now the last step is adding heat, and we said that heat means I'm losing carbon dioxide or water. We stated in chapter 17 the rules for losing water and losing carbon dioxide. Please refer to that. So in order to lose carbon dioxide, I need to have 2 carbonyls that are separated by 1 carbon. And one of the carbonyls needs to be a carboxylic acid. So again, to lose carbon dioxide, I need to have 2 carbonyls separated by 1 carbon. And one of the carbonyls needs to be a carboxylic acid. In this case, I would lose CO2, a carbon dioxide in this case. So you're going to go ahead and lose carbon dioxide, and the hydrogen that is remaining over here will add to this carbon, and you are going to end up getting your product. Let's have another example over here. So we are doing 2 equivalents of the base in presence of the polar protic solvent. Always use polar protic solvent here, so you are forming your thermodynamic product. But we have over here 2 types of alpha hydrogens, by the way. We have alpha hydrogens between the 2 carbonyls, and we have an alpha hydrogen over here for the ketone. So we know that these alpha hydrogens are more acidic than this alpha hydrogen over here. So this is why the base is going to target these alpha hydrogens, is not going to target this hydrogen at all. So these are going to be more acidic. I am using 2 equivalents, so I'm using that base twice, meaning that I am going to take both of these alpha hydrogens one at a time. So let's do one at a time in there. Let's do the first mole of the base. It's going to take the alpha hydrogen, make the enolate. Once it makes the enolate, then it's going to come and attack the alkyl halide. Notice here I have an alkyl dihalide in there, and I have 2 alpha hydrogens, and I have 2 bases. So there's a big possibility over here that I am closing and I am forming a cycle over here. So you're forming your nucleophile there. That nucleophile is going to come and attack the first partial positive carbon. SN2 reaction, bromine is going to leave. So what you did over here, you alkylated the alpha carbon in there. So I added 1, 2, 3, and 4 carbons and a bromine. We're going to do another mole of the base, form the enolate again. Now we already have the alkyl halide. This is an intramolecular now alkylation. So this is an intramolecular alkylation. So now the nucleophile is going to come, attack this carbon, bromine is going to leave, and see I'm going to form a cycle here of 1, 2, 3, 4, and 5 membered rings in there. Close the cycle, please. And this is going to be your 5 membered rings. If you want, you can go ahead and number. So it's going to be 1, 2, 3, 4, and 5. So I know that I would need to draw 5 carbons on the alpha carbon. Okay, because both are added on the alpha carbon. Now I'm not done yet. Whatever I did are steps 1 and 2. So let's go ahead and do step 3 in there. So with the step 3, I am doing hydrolysis of the ester in basic medium, and then I am adding the acid and heat. So hydrolysis of ester in basic medium is going to turn the ester into the carboxylate. And then I'm going to add the acid. This is going to be carboxylic acid now. Heat. I do have the case where I have two carbonyls and these are separated by one carbon, so I can lose carbon dioxide and then lose the carbon dioxide, add the hydrogen to this carbon, and here you go, you get your product. Because you can keep adding reagents as you go. So here, I can go ahead and reduce the carbonyl by sodium borohydride into an OH. After that, I can add multiple steps in there. I can do I can add HCl. So if you add HCl, you're gonna substitute the OH with the chlorine and so forth.